Thank you, Don. So it's a real fun time to be playing with hardware these days. And since the topic of this conference is agents, I thought I'd give you an example of an agent that one of our folks in our Toronto AI lab built. It's called Elegante, and it's basically a second-year graduate student doing computational chemistry. So if you have a question like what is the activation energy of caffeine, caffeine being very important to me this morning, you can give it this question, and you see the hierarchy of agents there, that little tree structure. Each of them, is an LLM with some state that's been, through a combination of fine-tuning and a prompt, given a task. So it will figure out how to generate the geometry of the molecule, optimize the geometry, submit a Slurm job to run a densital functional theory computation to actually do the calculation, and then post-process that and ultimately give you the answer. And this is an example of what you can do, with agents. So let's zoom in a little bit. And each one of those agents in the tree, the heavy work is done with the LLM, possibly with a chain of thought or tree of thought to give it some reasoning performance. But it's also very effective because it has tools, right? So the tools are, running the quantum chemistry simulation or doing a geometry optimization. But a tool can be as simple as a calculator. If you want a LLM to do some calculations for you, you're better off with like a 1 billion parameter model attached to a calculator than you are with a trillion parameter model trying to do that calculation just with the language. And so it's a very powerful thing to take that LLM and couple it with a little bit of internal state and memory and a policy and a bunch of tools that can be accessed. But this session is about infrastructure. Let's talk about what it takes to run one of these agentic models. And I'll start with some motivation. Deep learning really takes three things. It requires algorithms, as illustrated by the figure from the AlexNet paper on the bottom here. It requires data, as illustrated by the ImageNet photo on the upper right. And it requires hardware. You can think of this as sort of air, fuel, and spark, right? Once you have the air and the fuel, you need the spark to ignite it. So the thing that was here first, think of this as the air, were the algorithms. Deep neural networks, convolutional neural networks, training them with stochastic gradient descent and backpropagation were all known in the 1980s. In fact, I took a course when I was a graduate student at Caltech from John Hopfield in 1984, where I learned all this stuff. I got to build these neat little models, have them do really toy problems, and I concluded that this will never be practical because it requires so much more compute than we have today. Well, things have come a long way since 1984. We have a lot more compute. But the algorithms were around in the 1980s. The data started coming around in the early 2000s with the Pascal data set and then the ImageNet data set. And so they were around still for roughly a decade before things really took off. The spark that ignited that air and the fuel that were sort of sitting around waiting for the last missing ingredient was hardware that was fast enough to train a reasonable sized model on a reasonable sized data set in a reasonable amount of time. In this case, the AlexNet model on the ImageNet data set in roughly 2 weeks. And that was done with a pair of our Fermi generation GPUs. And then things really took off. And the way they took off is a factor of 10 million over the last decade in terms of the number of floating point operations required to train a state-of-the-art model. And there are really two very distinct trends. I could have drawn one line through the whole thing. You can draw a line through any set of points. But there are really two distinct trends here. During sort of the era of people building vision models, which is sort of the blue line here, starting with AlexNet and running up through ResNet and things like that, the growth rate was about 3 times per year. And even that is a pretty heavy lift. But since the Attention is All You Need paper came out in 2017 and people started building transformer-based models, the slope has been 16x per year, which is very, very tough to keep up with. And so as the people who build the bulk of the hardware that's used to train these models, we feel a big responsibility because in many ways the advancement of models is gated by the performance of hardware available to train them. And we feel a lot of pressure each generation to increase the performance both of a single GPU and the ability to scale up to more GPUs to meet that. So how did we do that? So this plot sort of shows the evolution of NVIDIA hardware for running deep learning over basically the last 12 years. And Blackwell is up enough that I didn't want to distort the rest of the graph by putting it on there, but it's up at 20,000 equivalent tera operations per second. We started with the bottom left corner here is our Kepler generation. This is actually the GPU after the one that was used to train AlexNet. That was the Fermi generation. Each GPU is named after a scientist. And Kepler wasn't designed to do AI. When we really made the decisions and locked down what was going to be in Kepler, we were focused on computer graphics, which needs 32-bit floating point, and scientific computing, which needs 64-bit floating point. And both of those are vast overkill for deep learning. But I kicked off our first project, actually before the Keplers were around. I kicked it off in late 2010 to basically replicate Andrew Ng's experiment finding cats on the internet on GPUs. And in doing that, we really convinced ourselves AI was going to be a big thing. We needed to start putting features into our GPUs for AI. So in the next generation, it was too late to catch Kepler at that point, but the next generation we put in support for 16-bit floating point and also put in dot product instructions. And I'll explain a little bit why that's important later. And so in the Maxwell and Pascal generation, it's really the same core GPU architecture. We had FP16. The next big jump happened in the Volta generation, where we realized that we really had to start amortizing out more of the cost of an instruction. Dot product was an improvement over floating multiply add, but matrix multiply was an even bigger improvement. So we put matrix multiply instructions into Volta. The HMMA, half precision matrix multiply accumulate instruction, multiplies two FP16 4x4 matrices together and sums the result into an FP32 matrix. The marketing people didn't like HMMA, so they called it tensor core. And then in the Turing generation, we had the integer matrix multiply accumulate instruction. In the Ampere generation, we added sparsity, and in Hopper, we added FP8, and in Blackwell, FP4. So where does the performance come from? And it's interesting because during the period of time when everybody was using CPUs, the bulk of the performance came from process technology. Moore's law was really about process technology, allowing you to build a faster CPU, basically doubling the performance every couple years. That has been dead for probably close to 20 years. And really, it died with the end of Dennard scaling, the constant field scaling of devices in 2005, when we stopped scaling supply voltage with gate length. And so over this entire period of time, from Kepler through Blackwell, what we've gotten from process technology is a factor of about 3x out of a total of about 4,000x. So where does the rest of that come from? Well, the single biggest gain in performance has come from number representation. So starting with FP32 in the Kepler generation and going down to FP4 in Blackwell has given us a factor of 32x. And to go to the int8 in FP8 and Hopper has given us a factor of 16x. And it's quadratic because when you do these operations, the dominant operation is multiply, and when you do a multiply, think about doing long multiplication by hand, you generate an array of partial products. So you have a number of partial products that's quadratic in the number of bits in the operands, and so the energy of the multiplies goes quadratically. The next biggest gain has been coming up with complex instructions. I'm actually going to jump ahead a slide, and then hopefully I'll be able to back up. If you look at how much energy it takes to do, and I've normalized all this to 45 nanometers to sort of not leak any information. Our energy numbers now are like an order of magnitude smaller than these. But anyway, to do a half precision floating multiply add, an FP16 floating multiply add in 45 nanometers takes about 1.5 picojoules of energy. But to fetch that instruction, decode it, fetch the operands, and store the results takes about 30 picojoules of energy. So the overhead is 2,000%. You're spending 20 times as much energy on overhead than you are doing the operation, kind of like a big corporation. If instead of doing a single floating multiply add, you do a dot product, now instead of doing 2 arithmetic operations, you're doing 8, right? So I've reduced that overhead by amortizing it from 20x to 5x. And continuing this, when you do the matrix multiply instructions, with the half precision matrix multiply, the overhead is now just 20%, 22%, and with the integer matrix multiply instruction, that's actually doing 1,024 operations on a single instruction, it's down to 16%. And in today's GPUs, that number's around 11%. So we've worked really hard to amortize the cost of instruction overhead out. If you look at that over this chart of where the gains have come from, that's given about 12.5x right? Not as big as the 32x from number representation, but still a very, very big factor. You multiply those together, and that's almost a 400x improvement. Then comes process technology that's given us a 3x from Kepler through Blackwell, and that's going from 28 nanometers down to 4 nanometers. And if you look at this chart, it's actually color-coded. It's hard for me on the monitor to see, but the black is 28 nanometers, the green is 16 nanometers, Ampere is I'm trying to remember, 7, and then we have 5 and 4. And so, going all the way from 28 nanometers to 4 nanometers, only a 3x gain in energy per operation. Going to the Ampere generation, we introduced sparsity, that we can basically, as long as you insist that out of every 4 elements of your matrix, no more than 2 of them are non-zero, we have very efficient implementation of structured sparsity, and that gives us a 2x boost in performance. And then on Blackwell, it's cheating a little bit, but it's really 2 GPUs. We have 2 reticle limited die that are on one package that we call 1 GPU. And so we essentially doubled the performance by doing that. It did not improve the performance per watt, though. So I talked about complex instructions. The other thing we had to do, so we basically got essentially 1,000x of that 10 million that we needed to support the growth in model demand for training from making the GPUs better. The other 10,000-fold comes from using more GPUs. And there are several axes to the parallelism that we use here. The first split is between data parallelism, which is sort of into the page on this chart, and model parallelism, which is the x and y axes on this chart. Data parallelism is easy. You take your training data set and you break it up into batches, and you dole these batches out to different groups of GPUs, and they basically operate independently, so it requires very little communication to do this and relatively modest synchronization overhead to do this. And then when you finish a batch, everybody sends their results together, so you can sort of combine the difference in weights from that one batch to the next. So everybody learns not just from their batch, but from everybody else's batch as well, and then you do the next set of batches. So data parallelism is easy. What's harder, but which you need to do also these days, is model parallelism. And model parallelism here we split across 2 axes as well. The first is pipeline parallelism, which is the y-axis here. So if you think about a typical transformer architecture, you have a number of layers. Llama 70B, I think, has 80 layers. And so you can basically take some number of layers, put them on one set of GPUs, some number of layers, put them on the next set of GPUs, and pipeline the activations through those. And then within each layer, you can do tensor parallelism. You take the matrix multiply you're doing, and you basically split that matrix up over a number of GPUs to get more parallelism. So by doing these things, we've gone over the years from training AlexNet on a pair of GPUs to a typical training cluster these days, maybe 100,000 GPUs running a single training job to train a, there's no way that I have talked for 15 minutes already. You need to start my timer when I started, not when I was supposed to have started. I understand how Berkeley Standard Time works here. Let me talk a little bit about software. So anybody can build a matrix multiplier. Back when I used to teach the introductory logic design course at Stanford, I think I could have assigned it to my class, and they would have produced a pretty good matrix multiplier within a week. But it takes a lot of software to make it useful. And in NVIDIA, we provide the software stack starting from the lowest layers, cuDNN, and then TensorRT that does the scheduling and packs layers of models together to avoid overheads. And then finally, verticals for things like self-driving cars and robotics and computer vision. But it's also critical to think that over time, the software actually improves the performance, because it's really critical that you get the software very, very fine-tuned and correct. And one good way of measuring performance here is to look at the MLPerf benchmark set. I think it's really it's an independent agency that publishes benchmarks and has pretty good rules about how to run them. And so people who make vast performance claims and don't have MLPerf results, I tend not to believe. But from one generation of MLPerf to the next, which is typically over a 6-month period, we'll see things like a 2.5x improvement in performance on the same hardware by improving the software. And this gives you an idea of how critical good software is for this. So let me, in whatever time I have remaining, which I think is more like 10 minutes, let me talk a little bit about future direction. So one thing we do to try to focus our efforts on where to put effort is to look at the best we can do today and ask, where is the energy going? And this is a pie chart, not from a GPU, but actually from an accelerator we build in NVIDIA research. And what you can see is most of the energy, that big blue area on the left side, goes to math. So basically, we still have to make the math better, and that means better number representation, exploiting sparsity, not just on activations like we do today, but not just on weights as we do today, but on activations as well, and also more aggressive sparsity. And then the things on the other side have to do with memory and data movement, and there are a number of things we can do there as well. So let me present a couple snippets, and then I'll wrap up, since the timekeepers here are not letting me do Berkeley Standard Time. One big message is that whatever number representation you pick, you want to make sure you fit the set of data you have to represent with that representation correctly. And what most people do is shown on the left side here, where they take the biggest number they need to represent and the smallest number they need to represent, and they pick a scale factor that fits that range of numbers into their number system. And if you do this, you have very large quantization noise, and you have no clipping noise because you're not clipping. The other option you have is to say, well, these really big numbers and really small numbers are outliers. Let's forget about them. Let's pick a maximum and minimum that are much tighter. And if we do this, my quantization noise goes way down, but now I've introduced some clipping noise. And you can pose this as an optimization problem. I won't go into the math here. But if you look at the graphs, on the very far right side of these graphs is what most people do, where you represent the whole number line. So you have a lot of quantization noise, very little clipping noise. And as I move to the left, I basically am trading quantization noise for clipping noise to the point where they're both equal, and that's the minimum point on each of these curves. And if you look, say, at the upper right graph here, the weight layer at 45, you're actually getting the same mean squared error that you would get with 4 bits that you would normally take 6 bits to get. So you're basically getting 2 bits of precision by doing optimal clipping. Another thing you can do is decide what set of numbers you're going to scale. And the way NVFP4 works, the way we're able to get performance out of 4-bit floating point, even for training, is by, instead of scaling a whole layer, which is what's conventionally done, we scale a vector of 16 elements. So with a smaller set of things to scale, we can basically scale it much more effectively and get much better performance. So let me talk about the interesting stuff before they drag me off the stage here. So if you look at LLM inference, there are really 2 very distinct phases. The first is a prefill phase, or context phase, where I take the entire prompt, not just the prompt you typed in, but that and the system prompt and any documents that are loaded by RAG. And there's an enormous amount of parallelism as I process all those tokens at once to produce the contents of the KV cache and the first output token, in this case, yes. But then I get into the decode phase, which is an autoregressive phase. Every token depends on the preceding token, and I've got to go through all 80 layers if it's Llama 70B and more for some other models. And it's very latency sensitive, and it's also very bandwidth sensitive, because I have to read the entire model for each token. Every one of those 70 billion or 405 billion parameters has to be read. And these days, you don't just do that once, but before you give a token to the user, I go through a chain of thought, running that LLM multiple times, or even a tree of thought where I'll do things in parallel and then prune down what my final answer is. Let me skip over the agent here. And what this does is it really drives very different demands for the hardware you use for the decode phase, the prefill phase, which is very math limited, right? You have lots of parallelism. You can batch things up. You can crunch these tokens out. And it's not very sensitive to latency. And the decode phase, where because it's autoregressive, it's very bandwidth limited. I got to read the whole model every token, and very sensitive to latency. And so it drives very different demands, and you see deviation in the hardware generations for things that are optimized for prefill and optimized for decode. The other thing you have to be aware of is that models are constantly evolving. This is some figures from the DeepSeek paper. The Kimi stuff just came out. And people are coming up with really clever ways of optimizing the attention process, using mixture of experts, so you can have a trillion parameter model but only touch maybe 20 billion parameters on each token that goes through. And by doing this, it means you need very programmable architectures. You don't want to hardwire your stuff, or somebody will come up with a model that you can't run. So let me wrap up here. I don't think I've used a full 20 minutes. We started late. They're trying to get on time by cutting my time short, and I don't like that. So anyway, to wrap up, deep learning was enabled by hardware. We had the air in the fuel, the algorithms and the data, and it wasn't until the GPUs came along and provided that spark to ignite that mixture and start our current AI revolution. Since then, we've been gaining progress in deep learning because it's taken ever more capable hardware to train these larger models on larger data sets, a growth of 10 to the 7th in demand over a 10-year period. The way we've done this is we've increased the performance of single GPUs by 1,000x in 10 years and by about 4,000x in 12 years. And this has mostly been through number representation and complex operations. Process technologies played a very small role. Software is absolutely critical to make these things usable and to realize the performance of that hardware. And I've given you some glimpses of things that we're doing to do more with less, including optimal clipping, vector scaling, and I had to skip over the sparsity. And so the current challenges I think we're facing is with disaggregated inference, figuring out how to handle the decode phase, which really stresses our current hardware in terms of latency and bandwidth, and then being able to handle chain of thought and tree of thought and agentic models that really drive up not just the amount of computation, but really also the demands on throughput, because if for every token you give the user, I've got to run 10 tokens through a chain of thought. That means if I want to deliver 100 tokens per second to a user, I've got to have hardware that can do 1,000 tokens per second. And we have to do all of this in an environment where every day we see papers popping up on arXiv with clever models, new ways of doing attention, and things that really require that we be agile and have very programmable hardware. So thank you very much.